what I'd like to do next is talk about surfaces of revolution. So this is a special class of surfaces that are really nice to describe. So let's start with equations, parametric equations. So we can write them in two ways. One way would be to write x is equal to some function c1 of t, and y is equal to some other function c2 of t. We can also write these in a simpler form as x is equal to t and y is equal to f of t for some interval I. So in the second case, we can describe maybe like this curve. This looks like it's a function. Okay, and I picked one of our examples later to be exactly something that looks like that. However, if we want to do things in the first form, if you've played around with polar coordinates, you know that you can have all sorts of intersections and have way more interesting curves. So for example, I remember recently I was doing like a petal. Okay, not the prettiest petal, but you can have, pretty cool things if you allow intersections. So what we want to do next is, I'm going to require that the y-coordinate is always positive, or at the very least non-negative. And surfaces of revolution, what they are defined to be is you take a curve and you take an axis and then you revolve them around the axis. So I am going to say my axis of revolution for these problems is the x-axis. Okay, I could have chosen any of them. I just decided I like it when it looks like it's on the x-axis. So what I like to do is I'd like to draw a little twirly thing here that is telling you the axis of revolution. So let's draw that on all of these pieces here. And I have some curves already drawn. And let's see what kinds of surfaces we can get from these revolutions. So in the first example, we have, this looks like maybe a hourglass on its side. Okay, it looks really nice, and I drew a little tangent plane at a point on it. So maybe by imagining that tangent plane moving around, you can convince yourself that it looks like everywhere the tangent plane looks fine. The next example is kind of cool. It looks like a little octopus maybe in the xy plane. When you do the surface of revolution, you get this funny shape, and it looks kind of like you have little trumpets, so maybe it's hard to tell, but you can actually look inside here. So these are little open holes where you can enter inside of the surface, and you have these kind of like little balloons on the top and on the bottom. So if you want to look at this, most of the places seem to have a nice tangent plane as well. I'm struggling to find somewhere bad, but of course, once we start having self-intersections, we can run into problems. So this is failing our one-to-one property. Now, when we look at the surface of revolution, it looks like we have kind of like three balloons, basically. And here I actually have the curve touching the x-axis, so when I revolve smoothly, it actually makes no problem over here. So if we actually look at the point corresponding to maybe here, in terms of a surface, this certainly looks like it has a nice tangent plane. Even though it seems like maybe it might lead to some trouble, it actually doesn't. So that's kind of neat. However, we do see that there's points where there's no such reasonable notion of tangent plane. I called those the bad points. Alright, so you can get quite a lot of interesting curves from just this class of surfaces. So let's derive the parametric equations for the surface. Let's visualize this in the following way. So if we look at our surface of revolution, so we have this plane here, but really this isn't part of our surface. I just like it because it visually imagines sweeping that out. And really what you're keeping track of is just the outside. Of course, you can do the volume of revolution and then figure out if maybe you can come up with the formulas for that. But that's a separate problem altogether. We want to deal with the surface. So to do that, I kept my x-axis in that location, which means I'm going to keep my y-axis here, and my z-axis will point in this direction. So in this case, if I'm going to do it like that, I'm going to say that this is my z plane and this is my y plane. And we'd like to come up with how to parametrize this kind of hourglass looking shape. So really I'm focusing maybe these are supposed to look more or less the same. So okay, let's start with the equation of a circle. But we're in the yz plane, so it should look like y squared plus z squared equals r squared. Okay, we all know that. Then if we parametrize it, we can write this as y is equal to r cosine theta and z is r sine theta. Okay, so now we're going to adapt it to, so let me write it twice. I'm going to write it once for when we have the formulas in terms of C1 and C2, and also when we have it in terms of t and f of t, because they're both kind of nice to write. They're not so bad. All right, so let's do it this time. So what is it that we want to use? So let's look at C1, C2. Remember, this is going to be, so this is my y coordinate, so that means this length is actually C2 of t. If we use the second parametrization, then the y coordinate here tells us that this is going to be f of t. Alright, so what that does, and that's going to give us the radius of our surface of revolution. So if we kind of look at this purple piece, let's maybe draw one line segment from the x-axis to the surface of revolution. The radius is going to be given by the second function of our parametrization. So if we write this down, we'll use that for our radius, C2 of t cosine of t, cosine of theta, and we'll use C2 of t sine of theta. So it's the same radius, C2 of t. Okay. Alternatively, if I use this second version, I can use f of t for my y coordinate, and this one looks even nicer in my opinion. It looks like f of t cosine theta, f of t sine theta, but they're really the same thing. It's just the first one's more general. Alright, now that gives me the y and the z coordinates of my coordinate functions for my surface of revolution. What about x? X is the easiest motion to describe. We're just moving in this direction. So with that in mind, we want to write x, and I should say note. X is equal to, well, I can have two choices here. We can either write it as C1 of t in the first form, or simply t. Alright, well, that gives me my parametrization. So let's write it down. Let's write it down as x of, and instead of writing the variables u and v, it seems like I very naturally have theta here as my angle of rotation, and I also have t moving in the x direction. So let's write these in terms of t and theta. Okay, and then let's write these as, our first function will be x, so we can write this as c1 of t. Our second function will be y, which we write as c2 of t cosine theta. Our z function will be c2 of t sine theta. So that's one of the ways we can write this. Let me pick a different color to write it in the other way. What color do I like? I don't know, pink. Okay, for the other form, this could be where our x-coordinate, let's pick it when we use t as our x-coordinate. Then our y will be f of t cosine of theta. And the z-coordinate will be f of t sine of theta. This video, we have now our formulas here, and let's even highlight. This is a nice little formula to have. Okay, so we have the derivation of a surface of revolution in parametric form. Alright, we're now ready to do some of the computations for a surface of revolution. So I am going to use our second parametrization here for a surface of revolution in the variables t and theta. So I also have it written down here. So let's just jump right in. Let's start computing the matrix of partial derivatives, dx. So let's start with x of t. So we're going to take the derivative of each of these functions. Okay, so first let's take the derivatives with respect to t. What is this? This is 1. Okay, that's it, folks. It's really that simple. What about our next function? So cosine theta and f of t, if I take the derivative with respect to t, I'm going to get f prime of t cosine of theta. And if I take the last derivative, okay, the last function with respect to t will get the derivative of f sine theta. Okay, this is x, the partial derivatives with respect to t of the 3 coordinate functions. Why don't we do the derivatives with respect to theta next? Alright, so the first function with respect to theta is going to be 0 since t and there's no theta. Alright, what about our next expression? So this time f of t is independent of theta, so we're going to get f of t times cosine theta. The derivative of that is negative sine of theta. Alright, and what about the derivative of the last piece with respect to theta? F of t is left alone, thought of as constant, and the derivative of sine will be cosine of theta. Okay, so that is our dx. Why don't we move on and start computing the first fundamental form? Okay, so why don't we start with taking the dot product of x of t with itself. Okay, what do we get? So x of t times x of t. So first component squared, so 1 squared plus the derivative of f cosine theta quantity squared plus the derivative of f sine of theta quantity squared. And if we simplify this expression, we can factor out the f prime squared. And again, what else? The Pythagorean identity will lead us to the following. 1 plus f prime of t quantity squared. Alright, so let's write our first formula here. So 1 plus f prime of t quantity squared. Now let's compute the derivative of x of theta with itself, the dot product of that with itself. So if I want to do that, I will consider this next column vector, and let's compute its length. So we're going to get 0 squared for squaring the first component, plus, let's square the second component. This will be f of t times negative sine of theta quantity squared times f of t times cosine theta quantity squared. So let's take a quick look at that and see if it simplifies. And it does. We're going to get f of t squared. So that is theta theta, so that's going to go in this component down here. So it's f of t squared. Alright, cool. Now we have to compute the derivative of the dot product between these two vectors. So for that one, I like to think of them like this. So we need to multiply these two components. So let's go down here, x of t dot x of theta. That's going to be 1 times 0 is 0, plus, looking at the next piece, we're going to get, what are we going to get? We're going to get, let's write f first, f prime, and then we're going to get cosine theta and negative sine theta. So let's put negative cosine theta times sine theta. Alright. What about the last piece? So if I take the dot product, we're going to get plus parentheses. Let's write f of t, f prime of t first, and then we're going to get cosine theta, sine theta. This time, however, it's positive, and then when I add up all of these pieces, we get 0. So there is our matrix of the first fundamental form. Time to compute the determinant. We multiply these two pieces, and then take the square root. So we are going to get 1 plus, and now let me use square brackets, f prime of t square bracket squared, parentheses, and I forgot an extra parentheses here. Okay, all right, times f of t squared. See, f of t, if you remember in my assumptions, I actually required f of t to be positive. This was so that it didn't touch the x-axis. So just keeping track of that, what we're going to do is we can take f of t outside and get 1 plus the square root of f prime of t squared. Okay, there is our determinant. Okay, going back to our area formula, we have the double integral over u of the square root of the determinant of gij du dv. So once we adapt everything to our problem, so instead of u and v, we are using t and theta, we're going to get a double integral of f of t square root of 1 plus the derivative squared. Okay, and let's say maybe dt d theta. All right, so as before, let's do our variable t first. What is it? We don't know what the interval is, so why don't we just write it like this? Over the interval I, whatever that is, since that's our t. And our variable theta, this one, if we double check how I defined it, it's going to be 0 to 2 pi. So take a quick look at that integral, and hopefully the first thing that jumps out at you is that there is no dependence on theta whatsoever. So the integral of d theta will produce a 2 pi. And this gives us the final form. I'm going to write it as the integral over the interval I, whatever interval we'd use to define our function. And this is our formula for the surface area of a surface of a revolution. Okay. Cool. That wasn't so bad. Time for some examples. Alright, so I even have a little exercise here if you'd like to do it in the other form. So, what is a wormhole? So, I'm going to talk about these from the perspective of geometry, not necessarily physics. So, wormholes to geometers is essentially a piece of a torus that is cut and attached back to the surface. I also call these tunnels. So let's draw a picture and let's see about maybe what kind of things we're talking about. So let's say we have some sort of funky surface, M, over here. What we want to look at is, let's say we have two pieces of our surface, maybe over here, little tiny disk in our surface, and maybe another region over here where we have another little disk. So a wormhole intuitively is what we're going to do is we're going to remove those little caps. So as long as they're small enough, they'll look like a little piece of a sphere maybe, or a little piece of the plane. And what we'll do is we'll replace that with something that looks like a tunnel. So I like to draw it like this. Okay, so let's say we have a nice long thin tunnel. Okay, and this is supposed to represent something that looks like a little piece of a tube. Okay, tube, torus. Hope you forgive me. Alright, so the idea is it should look something like this to begin. Let me just draw a piece of it where you want to be able to glue this piece of the tunnel back onto your surface. Okay, and then you want another piece of it over here as well. So I like to visualize them cut off. So it's almost like you cut it for a specific reason. Because in my research, what I like to do is we constructed tunnels or these wormholes that were really, really, really short. Okay, so they've been known about since Einstein and Rosen constructed them in general relativity. However, in a lot of the topology literature, these can be very thin and long. That's why I drew it this way. And part of my dissertation, what I needed to do was modify the known constructions so that they can be very, very short. So if you imagine attaching these two wormholes together, what do you get? You get something that looks like a little piece of a surface of revolution. So that's why the wormholes naturally enter into surfaces of revolution for us. Okay, so in the next video, which will be probably pretty short, I will take a look at a couple examples, and I'm not really going to do any of the calculations. Okay, I lied. Let's go ahead and do them now. So you can go to this link, and I will just go to it since I have it open. Okay, so by the way, if you want the blank notes or the completed notes, I'll post these here together with all the videos once I'm done filming them. So let's hit this activate button. And I have a couple examples that I have programmed. Okay, so here I have the hyperbolic cosine function from -2 to 2. So you can kind of see if I rotate it just enough, you can see the blue curve. So you can see the surface of revolution. But it's really nice to kind of visualize the wormholes maybe in this way. This is how you might see them in, I don't know, in physics books or in popular science. It looks pretty cool. Now I chose hyperbolic cosine for a reason, which I'll talk about a little later. But let's look at another one. Let's look at a parabola. It's 1/2 x squared plus 1. Alright, so if we think about this as a curve, so you all know parabolas very well, it looks really similar to the hyperbolic cosine. The reason I chose hyperbolic cosine, there's actually some really nice properties about it that I won't get into right now. It's minimal surface, for those who know that. But this one is actually a pretty good model for a black hole. Since if you look at what's called Schwarzschild geometry, it's actually modeled with a surface of revolution with a parabola. Not this exact parabola, but with something that's a quadratic function. Alright, so that's pretty neat. Let's look at one more. I'm going to look at one more, and then in the next video we'll do some of the calculations. So for this one it's going to be 2 plus cosine, regular cosine, but I want to change the interval. So I'm going to do it from 0 to 2 pi. Alright, so here now we're looking at the surface of revolution for 2 plus cosine of x. Okay, so I really just shifted cosine up by 2 so that it doesn't ever hit the x-axis, and as I rotate it, this is kind of that hourglass looking wormhole that I kept drawing, viewed as a surface of revolution, and it's pretty fun to kind of visualize this. Alright, so there you have it. These are some wormholes, and this one is actually pretty close to the wormhole that I used in my dissertation. It's not really cosine. It's actually, but it actually looks pretty much exactly like this.